Waves and particles. Newton first described light as a group of corpuscles, particles, and was able to explain reflection, refraction, and dispersion. Thomas Young and others found a wave-like description was the only way to explain diffraction phenomena. James Clerk Maxwell described light as perpendicular magnetic and electric fields moving as a wave. Einstein brought back the particle model to describe the photoelectric effect. Physicists love symmetry. Light has been described as being both a wave and a particle. So since electrons were discovered and well understood as a particle, what could physicists be thinking about? Since light had been described both as waves and particles, Louis de Broglie in 1924 proposed that particles could be described as waves, with the wavelength equal to h, Planck's constant, over p, momentum. Thus, all particles, and by extension objects like baseballs and bowling balls, have a de Broglie wavelength associated with their motion. But since h is so very small, the wavelength associated with large objects is vanishingly small. De Broglie's equation relates an object's momentum to its wavelength lambda. This equation works for light with no mass and for large objects with mass. We can substitute P equals mv for the momentum, now of course that's for particles that have a mass, and use the following equation for the wavelength of massive objects, like electrons or the large objects around you, h over mv. However, for small particles, like electrons, their wavelengths are often 10 to the minus 10 meters, which are about the size of the atom, so one might expect that they could experience wave-like effects like diffraction and interference. De Broglie proposed that an interference experiment be set up with crystals and electrons to validate his theory. In 1927, Clinton Davisson and Lester Germer were studying how electrons bounce off a nickel surface. They were not trying to prove or disprove de Broglie. This was a separate experiment. During the experiment, an accident occurred, discovery by accident, that resulted in the scarring of the nickel surface here. Here's your target, electrons coming in here, and then they measured what happened to the electrons at various different angles. This scarring made it act like a three-dimensional diffraction grating. They were startled to find an interference pattern in the scattering. Electrons were diffracting and then interfering as if they were waves. This was the first experimental proof of de Broglie's hypothesis. Later on, the two-slit or double-slit experiment that showed light was a wave, as performed by Thomas Young way back in 1803, was replicated, but this time with electrons, where the de Broglie wavelength of the electrons was on the same order as the distance between and the width of the two slits. Electrons fired one at a time towards two slits showed the same interference pattern as light did when they land on a distant screen. This indicates that something like an electron wave, and that's a poor phrase, but it's hard to describe this, must go through both slits at the same time, which is something we can't imagine a single particle doing, but the data have been shown over and over to be valid. These photos show electrons being fired one at a time through two slits, probably one of the most famous collection of physics photos ever. Each exposure was made after a slightly longer time. It appears that individual electrons behave like a wave and pass through both slits. Each time you see a bright spot, that's an electron that passed through the two slits. And down here, that's the interference pattern that we saw with light. Each electron must be a particle when it strikes the film, or it wouldn't make one dot on the film. It would be spread out. See, here's all your little dots, and the same for each one of the other pictures. So this one picture shows that matter appears to act as a particle with the dots and a wave with the interference pattern here at the electron level. And you can click here to see an animated GIF. An electron is traveling at a speed of 3 times 10 to the 7th meters per second, 1/10 the speed of light. What is its de Broglie wavelength? We have our speed right over here and the mass of the electron here. Use the de Broglie wavelength equation to solve for wavelength. So lambda is h over mv. We plug in Planck's constant and use the value of Planck's constant in joules because mass is in kilograms and velocity is in meters per second. Joules agrees with these units. Electron volts does not. So here's the mass, and here is the speed. Crank out the numbers, and we get a wavelength of 2.43 times 10 to the minus 11th meters. A weakness of the Bohr model is that Bohr just stated, without an explanation, that an electron in an allowed orbit did not radiate. Physicists, and people in general, like to have explanations. De Broglie's wave theory of matter was able to relate Bohr's statement to a physical property of the electron. As long as the circumference of an orbit was an integral multiple of the de Broglie wavelength of an electron in that orbit, it would not radiate. This approach yields the same relation that Bohr had proposed, but it's still not correct. It remained for quantum physics to explain the true behavior of electrons. These are circular standing waves for n equals 2, 3, and 5. So what's happening here is at first the wave looks like this, then it looks like this, and it oscillates between those two shapes. Same thing for n equals 3 and n equals 5. As long as the circumference of the orbit matched an integral number of the electron's de Broglie wavelength, and the wavelength is determined by this guy here, it would not radiate. It also explains why its angular momentum is quantized.